So in this problem, we're asked to determine two quantities within a parallel circuit, particularly the branch current through the 2 ohm resistor, I naught, as well as the voltage across the 8 ohm resistor, V naught. And from the problem as it's presented in the worked examples, you'll notice that I've drawn in the voltage V naught across the 2 ohm resistor as well. And of course that's valid since in a parallel configuration, the voltage across each of these branches would be identical. And we'll see how that comes into play in our analysis. So you may be tempted by the fact that this is a parallel circuit to employ Kirchhoff's current law, and that's probably the easiest way to do it. Recall that Kirchhoff's current law is a signed algebraic equation. Therefore, we need to be careful to maintain our sign convention. I'll enforce Kirchhoff's current law on the node, which I've denoted by the dark circle, and I'll follow a convention that all currents into the node are positive and all currents out of the node, such as I naught, are negative. Doing that, moving left to right, I have a current of 6 amps in, I have a current of I naught out, I have a current of I naught over 4 out. And then finally, on the 8 ohm branch, I've marked in again from the problem as it's written in the work description, I sub 8 to denote the current through the 8 ohm resistor. So I'll just write that as I sub 8. And of course, by Kirchhoff's current law, that algebraic sum is equal to 0. So here I have an equation, one single algebraic equation and two unknowns. Of course, I can't solve it. You may be tempted as your next step to take that I sub 8 and write it in terms of the other quantity, which we wish to find, V sub 0. We can do that in terms of Ohm's law. That would just be V sub 0 divided by 8. So I didn't get any close to where I wanted to get, but at least I've expressed the single equation now in terms of the two unknowns which I seek to find. Note that also, based upon this observation which we've made in the parallel configuration of the circuit, we can actually relate V naught to I naught, which will allow us through substitution to get a single equation with a single unknown. Specifically focusing in on that 2 ohm branch, we can write that V naught is simply 2 I naught, which again is just a realization of Ohm's law. Substituting, we can say that 6 minus I naught divided by 4 minus, now for V naught we're going to substitute in 2 I naught, that factor of 2 cancels and leaves us with just I naught over 4 again, and that's equal to 0. So if you notice here, we have minus 1 I naught minus another half I naught, so that's just minus 3 halves I naught equals, I should say plus 6 equals 0, which means that 3 halves I naught equals 6. And of course, multiplying both sides by 2/3, we can isolate the unknown which we desire and find that I naught is 4 amps, as we saw in the worked problem example. And we can easily compute V naught, the other quantity which we desire, using the equation which we substituted in, which I've started above. It's just going to be twice the current I naught in the appropriate units, of course. So that'll be 2 times 4, or 8 volts. And we can be a little loose with our units based upon the fact that each of the quantities presented is in the standard SI unit, amps, ohms. By definition, any quantity which we calculate would naturally be in volts, any voltage which we calculate.